Okay, in this section, section 3.7, it's going to be the first section in this chapter where we are not going to be looking at differentiation techniques. So we've spent the first 6 sections of chapter 3 looking at ways of differentiating different kinds of functions, whether they be specific functions like exponential, polynomial, logarithmic, trigonometric, that kind of stuff, or more general cases where we're adding, subtracting, multiplying, dividing, composing, etc., different kinds of functions. So in this section, we're going to turn our focus toward applications of derivatives. And 3.8 will be continuing that. We'll still be looking at applications. So if you were to read through, which I actually encourage you to do, read through section 3.7 in your textbook, you're going to see that they cover a whole lot of different applications. There's physics, economics, biology, chemistry, things like that. There's all these different applications they cover. We're only picking a selection of those topics, 3 in particular that we're going to be focusing on in this section. But I still encourage you to look at the other applications just to get a sense of how useful the derivative is, because some of those applications will appear in other courses you might take, and it's just good to have some of those under your belt. So before we launch into this, I want to start with a recap of what the derivative is. Suppose you have some function y equals f of x, and suppose that the variable x changes from one value to another. Specifically, let's suppose it's increasing from x1 to x2. We use the notation delta x to represent that change. It's the distance between x1 and x2, which would be given by x2 minus x1. Okay? That change in x creates a corresponding change in y, which would be given by delta y equals f of x2 minus f of x1. When we take these two quantities together and form a quotient out of them, delta y over delta x, or using what they are equal to, f of x2 minus f of x1 over x2 minus x1, this result is what we would call an average rate of change. We know from even as far back as pre-algebra that quotients can be interpreted as rates of change. So in particular, this would be the rate of change in our function y equals f of x over the interval x1, x2. Okay? And we did plenty of this even as far back as chapter 2 in our book. Now, alternatively, we can also think of this slope, this quotient here, as representing the slope of a secant line passing through 2 points on the curve given by y equals f of x. In particular, if I'm calling those points P and Q, where P has coordinates x1, f of x1, Q has coordinates x2, f of x2, then this thing is simply slope formula applied to these 2 points. So here's an example. This black curve here is the graph of our function y equals f of x. And if this is the point P and this is the point Q that I just referenced, then the line connecting them, if I continue that line all the way through, would be a secant line, and its slope would be given by delta y over delta x, which is that average rate of change. If we then apply a limit to this difference quotient as we allow delta x to shrink to 0, that would be shrinking this distance between our x1 and x2 down to nothing, which brings that secant line all the way down to a tangent line. And after applying that limit, the slope that we get is that tangent line. Okay, so once again, the connection between derivatives as we use them in applications and derivatives as we visualize them in a graph is that the slope of this secant line represents an average rate of change over this interval, whereas the slope of this tangent line represents an instantaneous rate of change at that exact value, x equals x1. Okay, this is all review. We've covered all of this before, but the idea is to remind you of where the concept of the derivative came from so you can see why it fits into applications. So one application that we've already looked at, and we're gonna just dig in a little bit more to this, is the relationship between the position, velocity, and acceleration of a point or a particle moving along a line. In that case of a particle can be generalized to things that aren't necessarily points and particles, but still have a concept of position, velocity, and acceleration associated with them, like a car driving in a straight line or something like that. If our position, velocity, and acceleration functions are given by s of t, v of t, and a of t, respectively, then we have previously shown that those 3 functions are all related to each other by the derivative. A of t, acceleration, is the derivative of v of t, my velocity, and the derivative of velocity, which would make it the second derivative of acceleration, the derivative of my position function is velocity, which means the second derivative of my position function is acceleration. So these three have this relationship. Okay, so with that said, I want to look at a couple of examples involving this acceleration, velocity, and position concept. Starting with this one, we're given a graph, but we're not given an algebraic representation for this function. It says the graph of the velocity function of a moving particle is shown below. So specifically, we're thinking of the x-axis as representing time and the y-axis as not representing position, but representing velocity. Okay, so the first thing we notice is that the first thing we're asked to do is determine when the particle is moving forward, backward, or not at all. And when we say when, that's indicating that we're looking for times. Since my time is represented by this horizontal axis, we're going to be looking at intervals on that horizontal axis at which these different things are happening. So first of all, when is the particle moving forward? So when we talked about velocity previously on a one-dimensional line, we interpreted a positive velocity as meaning moving forward or to the right, typically, or we actually interpreted it as moving down when we made that vertical. For the case of like a free-falling object. But we're going to just interpret positive velocity as moving forward. Negative velocity is going to be interpreted as moving backward, whatever we've decided forward and backward to mean in this context. And then not moving at all is self-explanatory. So if this is the graph of velocity, when is this particle moving forward? Let's start with forward. Moving forward whenever the velocity is positive. And graphically, that would mean that we're looking at where this curve or where this graph is above the x-axis, because that's where that velocity is going to be positive. It looks like it happens from here to here. And that would be 1, 2, 3, 4, 5. So on the interval from 0 to 5, we are moving forward. And in fact, I'm going to make that a half open interval because it looks like as soon as we get to 5, if I'm trusting my eyes on this graph, our velocity gets to 0. As soon as we're at 5, we're no longer moving in the positive direction. We're not moving forward anymore. When are we moving backward? Actually, I'm not on B yet. Backward. Well, that would be whenever our velocity is negative. And let's see, that was 5, 6, 7. Once I get to 7 and I continue moving through time, it looks like my velocity graph is giving me negative values. So from 7 to 8, it looks like my velocity is negative, moving backward. I'm going to write that interval this way. And again, this parenthesis indicates that I'm not including the endpoint 7, because at 7, if I can trust my eyes on this graph, it looks like the velocity is 0, not negative. When is it not moving at all? Whenever something is not moving, in physics, we typically use the term at rest. So another way of asking this question is saying, when is this particle at rest? And that would be whenever our velocity is 0. It's not positive, so we're not moving forward. It's not negative, we're not moving backward. It's 0, we're not moving at all. And on my graph, I can see that occurs from 5 to 7, from time 5 to time 7. And we're not told in this problem what time is measured in. This could be seconds, minutes, hours, years, centuries. I have no idea, but this is the intervals that would answer that question. Next thing we're asked to do is sketch the graph of the acceleration function for this particle. Now, one thing I want to point out is that this is an unrealistic graph for the motion of a particle. And the reason for that is these sharp corners. What do these sharp corners actually mean? Well, if you notice, my velocity is increasing as I go from 0 to 1. So I'm getting faster and faster and faster, right? And then suddenly I go from kind of a sharp rate of increase in my velocity to just leveling out completely. The flat here for these 2 units of time, seconds or minutes or whatever they are, indicate that I'm not speeding up or slowing down. I'm still moving in the positive direction because I have positive velocity, but it's not changing velocity. So I'm not speeding up or slowing down. So that would indicate that I went from a relatively rapid rate of increase in my velocity to just suddenly not increasing at all. We would expect this to have a little bit more of a curve here to kind of see our velocity gradually change from rapidly increasing to not increasing at all. But with that said, you know, we're going to assume that this probably impossible situation is possible for this application. So if we want to graph the acceleration function for this particle, the key thing here is to remember that acceleration is the derivative of velocity, which means I'm looking at the derivative of this graph. Now, at each of these corners, the function will not be differentiable. We know that the graph, if the graph of a function has corners or cusps, then the derivative doesn't exist there. But everywhere else, it will exist. And the nice thing about this graph is we're working with straight lines. So making note that the derivative of a function means the same thing as the slope of that function, or a slope of a tangent line of that function at a given point, I can just use the slopes of each of these individual line segments to find my graph. So first of all, as I move from x equals 0 to x equals 1, delta x would be 1. That's the movement in the horizontal direction. My vertical direction, I appear to be going up by 3. 1, 2, 3. So that's positive 3 for my delta y, positive 1 for my delta x, and 3 over 1 gives me a slope of 3. So let's go like this. 1, 2, 3. So as x changes from 0 to 1, I have a constant slope of 3. The slope doesn't change along any of these points. So that means my derivative is going to look like a constant function. It's going to be horizontal. Okay. The open circle here represents the fact that there's a corner in the actual graph, so there won't be a point there. Okay. Next up, as I move from 1 to 2 along my x-axis, my change in x is 2, but my change in y is 0 because we are not going up and we are not going down from this point to this point. So 0 over 2 is 0. That means the slope of this function here, or the slope of this graph, is 0 for those two values. 2, 3, open circle, and my acceleration will be 0 for those values. I actually realize I'm going to have to go down a little bit further. Okay, next thing, as I go from 3 to 5, I can see that I have a negative slope. I don't think I gave myself enough space here. So as I go from 3 to 5, my change in x is equal to 2. My change in y is equal to negative 3. I'm going down 3 units from here to here. So that's negative 3 halves, okay? Or negative 1.5. So that's negative 1, negative 2, negative 3. Negative 3 halves would be right in between right there. So we're going to have from 3 to 5 a slope up here of negative 3 halves. And then once again, as I go from 5 to 7, 6, 7, my velocity is remaining constant. It's at 0, but it's a horizontal line, so it's not changing. And as we saw before, that indicates that our acceleration will be 0. We are not speeding up. We are not slowing down. Okay, I didn't make my axis long enough here, so I'm going to have to make this a little bit sloppy and extend that. And then we go from 7 to 8, at which point our slope is negative again. This time I have a change in my x equal to 1, change in my y equal to negative 3. So we're going to go from 7 to 8 with a slope of negative 3. Okay? Notice that my acceleration function has a lot of discontinuities, and that's part of what I was saying before, that this is an unrealistic graph. it doesn't really happen in real life that we instantaneously change our acceleration from 3 to 0. There's going to be a more gradual change in a realistic scenario. But this is what the graph of our acceleration function looks like. Okay, and we're going to use that to answer this question: when is the particle speeding up, slowing down, or staying at a constant speed? The way that we interpret speeding up, the way that we're going to interpret whether we're speeding up or slowing down is something we have to be careful about, because we have to take into consideration not just the sign of our velocity and the slope of it, because that's telling us whether we're speeding up or slowing down, but also whether the velocity is positive or negative. So it's not just a simple matter of saying acceleration is positive, that means we're speeding up, acceleration is negative, that means we're slowing down. We have to look at how acceleration changes from one value to another. And in this case, I could use my acceleration graph. I could also think of it using my velocity graph if I know how to interpret those slopes. So let's start with the speeding up question. My velocity is speeding up if it's moving away from 0. And that can happen in two different ways. I can move away from 0 in the positive direction. So if you notice from here, I'm going from 0 to 1. My velocity function is moving away from 0 in the positive direction. That means I'm gaining positive velocity as I go from here to here, which would cause me to speed up. That happens on the interval from 0 to 1. Okay, so I'm speeding up on the interval from 0 to 1, and then I stop, so I'm going to use that open parenthesis right there. As I move from 1 to 3, my velocity doesn't increase and my velocity does not decrease. So I'm neither speeding up nor slowing down over the course of this interval. So we're not going to look at that for this part. And then from 3 to 5 on my x-axis, the line segment is approaching 0, not moving away from 0. So that means I'm starting at a high velocity of 3, whatever units that would be given by, and moving toward a velocity of 0, which would mean I'm at rest. That means I'm slowing down over this interval, so we're not going to worry about that yet. Then again, I have from 5 to 7 a horizontal line segment, which indicates my velocity is remaining constant. In this case, it's constant at 0. So I'm neither speeding up nor am I slowing down here. Then finally, I have this negative slope here. But it's not just the fact that it's negative, it's that as I move from 7 to 8, the velocity of this particle is moving from 0, which means at rest, to -3, which means -3 units of velocity, but in the negative direction. So even though the slope is negative here, I'm actually speeding up. It's just I'm speeding up toward the left instead of toward the right, if that's how we interpret backwards and forwards. So from 7 to 8, I am also speeding up. Slowing down. We actually answered the other two questions in the process of looking at that whole graph. I'm slowing down as my graph moves toward 0, whether from this direction or from this direction. So from here, I'm moving, as x moves from 3 to 5, my graph is going towards 0. Okay, so from 3 to 5. We're moving towards 0. And then that's the only time I'm actually slowing down. So now I'm going to say not at rest, constant speed. Our speed is remaining constant when we're not speeding up or slowing down. That corresponds to these horizontal line segments. So I'm going to call that the interval from 1 to 3 and the interval from 5 to 7. Okay, oh, that was off screen there. So that's how we can answer those questions. We're going to do another example, and this is all we're going to have time for in this first part. But another example where instead of looking at a graph, we're looking at a position function of a moving particle where we have a representation for that function algebraically. So first thing it asks is if our position function is s of t equals 9t over t squared plus 9, what is the velocity after 1 second? To do that, I would need a velocity function, v of t, which is s prime of t. That's our relationship between position and velocity. Taking the derivative of this guy is going to require the quotient rule. So I do my low function times the derivative of my high function, 9 times t squared plus 9, minus high times the derivative of low, that's 9t times 2t, or 18t squared, all over t squared plus 9 quantity squared. Now that I have this, I can simplify a little bit. This thing up here would simplify to 81 minus 9t squared. And that's after distributing the 9 and combining some like terms. I could also factor my numerator, which would give me 9 times 3 plus t times 3 minus t. Okay. So remember, what we wanted here was a velocity after 1 second. Now technically any one of these three expressions can be used as my velocity function. I'm going to use this one here. So v of 1, I'm plugging a 1 in to get the velocity specifically at 1 second, would be equal to 81 minus 9 times 1 squared over 1 squared plus 9 quantity squared. Okay, so this is equal to, I got a little smudge there, 81 minus 9, which is equal to 72, over, here I have 1 plus 9, that's 10, squared is 100. Or if you prefer decimals, 0.72. And I know that my time is measured in seconds, but I'm not told anywhere where my units of measure are. I'm going to actually include that because I want to make sure you know how to use these units of measure. So the position function of a moving particle is given by s of t equals this, and I'm going to say meters. Let's say that our units for distance are measured in meters here. So that means my velocity would be measured in meters per second. Okay, that would be my velocity at my time t equals 1. Okay, next thing that we need is when the particle is moving in the positive direction. So remember, that means that our velocity would be positive. We're specifically looking for when v of t is greater than 0. And that's where I'm going to use this form of v of t. That implies that 9 times 3 plus t times 3 minus t over t squared plus 9 quantity squared is greater than 0. Okay, this little double arrow thing means implies that. This implies that this. Now, in algebra, you would have talked about how to deal with rational inequalities like this. And the way you want to think of this is that being greater than 0 means positive. So what does it take for a quotient to be a positive number? Well, you're dividing by something. So if my numerator and denominator are both positive, positive divided by positive is positive. If my numerator and denominator are both negative, negative divided by negative is also positive. If my numerator and denominator have different signs, one's positive while the other's negative, then this quotient comes out negative. So basically, we want our numerator and denominator to have the same sign in order for this to be true, both positive or both negative. Now, because my denominator is something squared, it can only be positive. That means that I am specifically looking for what it takes for my numerator to be positive, okay? And in fact, this 9 here, since it's already a positive number, is not going to change the sign of this thing, whatever it is. If this is already positive, multiplying by 9 will keep it positive. If 3t plus t times 3 minus t is already negative, multiplying by 9 will keep it negative. So I can simplify this a great deal by just writing this. As long as 3 plus t times 3 minus t is greater than 0, then this will be satisfied. So how do we then determine when this happens? Well, the way we typically handle this is we find the zeros of this function and then use that to partition a numbered line into subintervals. But there is one thing I want to pay attention to. See, if I have 3 plus t times 3 minus t equals 0, so I'm finding the zeros of that expression, that would imply that t is equal to plus or minus 3. But t represents time, and we only represent time in positive units. So the negative 3, even though it makes sense algebraically to have t equals negative 3, it does not make sense in this application. So I'm going to throw the negative 3 out. That means the only 0 that we're concerned with is 3. I do, however, want to consider the fact that time is considered to start at 0. So I'm going to include a 0 here. Okay? And then I have 3 here. So how do we use this number line? Well, what I'm going to do is imagine picking a test point in each one of these subintervals. So the interval from 0 to 3 and the interval from 3 to infinity. Plug it into this expression and see if it comes out positive or negative. So for example, if I took a 1, which would have belonged to the interval from 0 to 3, and plugged it in here, 3 plus 1 is 4, 3 minus 1 is 2, 4 times 2 is positive, right? So here, on this interval, my velocity is positive. What about from 3 to infinity? All I need to do is pick any number in that interval. Let's say 4. Okay, 3 plus 4 is 7. 3 minus 4 is negative 1. Positive times negative would be negative. So my velocity function is negative here. Okay, we know that our particle is moving in the positive direction anytime velocity is positive. So the answer to this question would be the interval from 0 to 3. I've been a little flip-floppy with my closed and open intervals. I'm going to just use a closed interval for simplicity here. I think an open parenthesis might be more appropriate, but I think it's also getting a little bit confusing alternating between those. So the closed interval from 0 to 3. What is the total distance traveled in the first 6 seconds? So this one is a little bit tricky because as time passes, so as we go from 0 to 3 to 6, according to our previous step, we saw a change in direction happen at 3. So in the first 3 seconds, our particle is moving in the positive direction. But then in the next infinitely many seconds after that, it changes and moves towards the negative direction. So what's happening here is my particle, I'm going to do this separately, is going this direction for the first 3 seconds, right? But then it's going to change direction and go that way for all time after that, but we're only interested in the next 3 seconds, from 3 to 6. Next 3 seconds. Okay? So we want to consider both of these quantities to be positive. I want to know, even though I'm moving in the positive direction here and negative direction here, the total distance traveled is going to be this positive distance plus this positive distance. And how do you find that distance? Well, the distance would be the change in position, delta S, right? So at first, let's write it this way. Dist in first 3 seconds. To make sure that this distance comes out positive, I'm going to use an absolute value. It's the absolute value of S of 3 minus S of 0. Okay? S of 3 minus S of 0, because this would represent the change in position over those first 3 seconds. What is this equal to? It's the absolute value of 9 times 3 over 3 squared plus 9 minus, and what I'm doing is I'm using my position function here, plugging a 3 in. Notice if I plug a 0 into this, I get 0 over 9, so it's just 0. Okay? What is this equal to? Well, that's 9 times 3, which is 27. 3 squared plus 9 would be 18. That reduces to 3 halves minus 0. And absolute value is still just 3 halves. Okay. Now how about the distance in the second 3 seconds? So this is from t equals 3 to t equals 6. I'm looking at the absolute value of s of 6 minus s of 3, because this is the total distance traveled as time changes from 3 seconds to 6 seconds. Okay, s of 6 would be equal to 9 times 6 over 6 squared plus 9 minus, we already found s of 3 right here, so I'm not going to redo the work. That's 3 halves. I'm kind of running out of space here. Okay, 9 times 6 is 54. This is 36 plus 9, which is 45. 54 over 45 would be 6 fifths minus 3 halves. Okay, this is going to come out to, let's see, this would be 12 tenths minus 15 tenths, which is negative 3 tenths, but then I take an absolute value and get a positive 3 tenths. So that means my total distance would be 3 halves plus 3 tenths. That's the same thing as 15 halves plus 3 tenths, or 18 tenths, or 9 fifths. And that's in meters. 9 fifths meters, or equivalently, I could call that 1.8 meters. So this video has already gone longer than I want it to go, so that means for part D, we're going to save that for the next part of this video.